What if you could take an old idea that was considered unsophisticated and inefficient and transform it into a modern machine just by adding an unexpected twist? That's what we're going to learn about today. The K-nearest-neighbors algorithm, also known as KNN, has been used in statistics since the 1950s. It's a very simple idea that was considered computationally expensive. But in the 1970s, something called the KD tree was invented. KD tree is short for K-dimensional tree, and its arrival turned out to be a game changer for many computer science applications, one of which was the KNN algorithm. So, what is KNN? And what's a KD tree? And are those Ks related? Well, let's find out. Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I'm your host, the Dabbling Doggo.
I dabble.
The best way to understand KNN and KD tree is to see a demonstration of it. So let's jump into VS Code and generate some plots. For today's tutorial, knowledge of Julia and VS Code is required. I'm also assuming that you're watching this entire machine learning playlist. In your VS Code Explorer panel, create a new folder for this tutorial. In the tutorial folder, create a new file called sl_knn.jl. Launch the Julia REPL by using Alt-J, then Alt-O. Maximize the REPL panel. Change the present working directory to your tutorial directory. Enter the package REPL by hitting the closing square bracket. Activate your tutorial directory. Add the following packages: nearest neighbors, plots, R datasets, and statspace. Type in status to confirm the version numbers. Exit the package REPL by hitting backspace. Minimize the terminal panel. Okay, let's get started. Let's start by loading some packages. I'll provide more information about the nearest neighbors package in a few minutes, but for now, let's just use it to demonstrate some concepts. We're going to use the plots package to generate a scatter plot with some random points to represent a two-dimensional feature space for demonstration purposes. Using a random seed is not required. I'm using it so I can reproduce my results. If everything went okay, you should see a scatter plot with 100 randomly placed data points. You can imagine that feature 1 is something like weight, and feature 2 is something like height, and the points represent the data that you've collected from 100 subjects that fall into one of two classes, say cat or dog. Now, say that you've received new data for feature 1 and feature 2 from a new, unseen subject, and you need to classify that unseen subject as either a cat or a dog, just based on the new featured data. Let's see how we can do that using KNN combined with a KD tree. Like the lib.svm.jl package, the NearestNeighbors.jl package requires your training data to be in a horizontal format, rather than a vertical format, meaning that each row should be a feature, and each column should be a sample. There are several different ways you can transpose your data in Julia, For the SVM model, we use the linear algebra standard library. But today, I'm going to show you how you can transpose your data using the permute dimensions function from Julia Base. As you can see, this matrix has 100 rows and 2 columns. By using the permute dims function, the matrix now has 2 rows and 100 columns, which is what we need. The NearestNeighbors.jl package comes included with a KD tree constructor. I'll explain what this is in more detail in a few minutes, but at a very high level, what the KD tree constructor is doing is taking your dataset and mapping it to a data structure that will make it extremely efficient for it to be used for analysis. This variable k is the k in k_nearest_neighbors. By using a value of 11, that means that we want to find the 11 data points in the training data subset that are the nearest to the test data point. The term nearest means different things to different people, and the NearestNeighbors.jl package supports several different ways to measure distance. But we're only going to use the Euclidean distance, which you'll recognize from high school geometry. So in this diagram, the Euclidean distance between point A and point B is 5 units. Let's generate a random test point in order to demonstrate KNN in action. When using the plots package, you need to enter the x-coordinate and the y-coordinate as a Julia array, even if it's just a scalar with a single value. You should now see a red dot, which represents your new test subject. You can see its nearest neighbors just by looking at this plot, but can you identify the 11 nearest neighbors? The first 3 or 4 may be easy to spot visually, but it becomes more difficult as the neighbors get further away. Let's see how we can solve this by using KNN combined with a KD tree. This KNN function returns the index numbers of the 11 nearest neighbors from your training data subset. It also returns the Euclidean distances measured between your test subject and those 11 nearest neighbors. Using the true argument means that you want the output to be sorted by the distances. Let's take a look at what this output looks like. So these are the 11 nearest neighbors to your test subject. The first column contains the index numbers of the samples from your training data subset, and the second column contains the Euclidean distance calculations. As you can see, the distances are sorted from low to high. While this may be useful information, it's still somewhat abstract. So let's see if we can show these 11 points on our plot. This code generates the x-coordinates of the 11 nearest neighbors. And this code generates the y-coordinates of the 11 nearest neighbors. You should now see the 11 nearest neighbors highlighted in yellow. Pretty cool, right? Now, let's connect those 11 nearest neighbors to the test subject. This plotting syntax is a bit tricky, even if you're an experienced user of the plots package, since connecting points on a scatter plot is not typically done. The first argument contains the x-coordinates for your test subject and one of the nearest neighbors. That second argument contains the y-coordinates for your test subject and one of the nearest neighbors. The plots package will connect those 2 points with a green line. The for loop will just loop through all 11 of the nearest neighbors, so you should end up with 11 lines. As a reminder, when using the plots package, you need to call the name of the plot in order to display any updates.
Wow!
Those green lines are the Euclidean distances that we saw earlier as floating point numbers. In order to reinforce what we just saw, let's repeat this process with a new random test subject. Go back up to line 49, or whatever line it is in your editor, and generate a new random test point. And then rerun all the code until you update the plot. You should see a new red dot in your plot representing a new test subject. These are the 11 nearest neighbors to your latest test subject. Your plot should now show these new 11 nearest neighbors highlighted in yellow. And now, your plot should show 11 green lines representing the new Euclidean distances from the latest test point to its 11 nearest neighbors. So conceptually, this is how the KNN algorithm works with a KD tree. Since you know the classification for everything in your training data subsets, you can use that information to find out the classifications of the nearest neighbors to any new test subject. So maybe the first red dot represents a cat, and the second red dot represents a dog. You can figure that out based on its proximity to other cats and dogs in the training data subset. While K nearest neighbors and KD trees are used for supervised machine learning, they may be used for many more applications. For example, they are used in computer graphics and in robotics. Anything that requires analysis based on measuring distances may benefit from using K nearest neighbors and KD trees. For a creative example of what's possible using the NearestNeighbors.jl package, check out this animation created by Cormullion using the Luxor.jl package combined with the NearestNeighbors.jl package. There's a link to it in the description below. Before leaving this section, I'm going to save my plot, since I'm always forgetting to save my plots for these tutorials. All of my code and plots are available in my GitHub repository. Okay, now that we've seen a high-level conceptual demonstration of KNN and KD tree, let's dive a little deeper into the details. The K nearest neighbors algorithm was created by Evelyn Fix and Joseph Hodges in 1951 while they were at UC Berkeley. The KNN algorithm was originally used in statistics. The K in KNN is an integer greater than or equal to 1, and as we've already seen, it indicates how many neighbors that you want to identify. The idea behind KNN is relatively simple. You take your test data point and measure the distance between it and all of your other data points. You sort the results from lowest to highest, and then select the neighbors starting from the top of that sorted list. While this idea is relatively simple and works well with small datasets, using the KNN algorithm is not practical for large datasets with multiple features. Imagine trying to calculate the distance between a test data point with millions of other points on a 100-dimensional feature space. Not only is that difficult for humans, it's also difficult for computers as well. The KD tree changed all of that. The KD tree was invented by John Bentley in 1975 while he was a PhD candidate at the University of North Carolina at Chapel Hill. Like the kernel trick used with SVM, the KD tree is like something out of science fiction. It's a generalization of a binary search tree. So, what does that mean? In my first tutorial series on this channel, called Julia for Beginners, I covered the binary search algorithm. In episode 110, I shared the code for a guessing game that you could play against your computer, where the computer tries to guess a number between 1 and 100 within 7 guesses. So how is that possible? Here's a visualization of a binary search tree for the integers from 1 to 100. I know that you can't see all of those numbers, but this tree diagram shows all the numbers from 1 to 100 mapped onto a tree. Let's zoom in on the path of trying to guess the number 42. A naive algorithm would be to start at 1 and then go through each number in sequence until it finds the number 42, which would take 42 guesses. The binary search algorithm starts at 50 and then asks, is the number lower or higher? Since 42 is lower than 50, the algorithm then guesses 25 and asks the same question, is it lower or higher? The algorithm continues this process of splitting the search region in half until it finally guesses the correct number. By following this algorithm, you can see that it quickly goes from 50 to 25 to 38 to 44 to 41 to 43, then to 42. That takes 7 guesses, which is the worst case scenario. As you can see in this tree diagram, you can guess every number between 1 and 100 within 7 guesses. When data is stored in a binary search tree, it makes it very efficient for your computer to go through large datasets. Now, this particular tree is an example of a one-dimensional tree. What if you could build a two-dimensional tree, so you could handle a 2-feature dataset? Or a 4-dimensional tree, like for the iris dataset that has 4 features? Or some other multi-dimensional tree with k dimensions. Having such a data structure would make it possible to search through large datasets with multiple features very efficiently. That's what a KD tree is. Like the K in KNN, the K in KD tree is also an integer equal to or greater than 1. But the K in KD tree represents the number of dimensions in your feature space. For example, 2D for a 2-dimensional space, or 3D for a 3-dimensional space. It's an unfortunate coincidence that the K in KD tree and the K in K nearest neighbors are both being used at the same time. But these Ks represent completely different values used for completely different purposes. In any event, combining the KD tree with the KNN algorithm transforms an otherwise inefficient algorithm into a modern tool with many practical applications, one of which is being able to use it for supervised machine learning classification. As we've already seen, we can use the NearestNeighbors.jl package for this purpose. The NearestNeighbors.jl package was created by Christopher Carlson, who is a prolific Julia developer. The NearestNeighbors.jl package is a pure Julia implementation of both the k-nearest-neighbors algorithm as well as the KD tree data structure. While both the libsvm.jl package and the decisiontree.jl package offer a plug-and-play experience for those wishing to use them For supervised learning classification problems, the NearestNeighbors.jl package is more like an API that may be used for many different applications. So, if you're an experienced Julia developer, the Nearest Neighbors package is great, since you can use it for anything you like. But if you're a casual Julia user, it may not be immediately obvious how to use it to solve machine learning problems. The KNN algorithm may be used to solve both regression and classification problems using supervised machine learning. If you want to use it for supervised machine learning classification problems, you need to do a little pre-processing work and a little post-processing work. But don't worry, we'll go through an example, so by the end of this tutorial, you'll know exactly what to do. Okay, enough with the backstory. Let's see the NearestNeighbors.jl package classify some data. In this section, we're going to use the iris dataset again as our motivating example to generate classifications using the k-nearest-neighbors algorithm combined with a KD tree. Let's start by loading a few more packages. StatsBase is a very useful package that I've covered in a previous tutorial on this channel. We're only going to use it for one function this time. Next, let's load our data. The rDatasets package loads the data as a data frame. Using the data frames package is great, but often unnecessary. So a lot of times I prefer using Julia's native data structures, like the matrix and the vector, which is what I'm doing here. This next bit of code comes from Huda Nassar, and I've used it in the past 2 tutorials. I'm just going to copy and paste it from a previous tutorial. Next, we need to identify the index numbers from the iris datasets that we want to use for training and for testing. Even though I set a random seed earlier, I need to set it again since I've already used some random functions. Now that we have the index numbers, we use them to split our data between training and testing. Like we did earlier, we need to transpose our feature data using the permute_dims function from Julia base. Next, we need to build our KD tree. Unlike the K in KNN, you do not need to set the K in KD tree since it's done automatically. In this case, the K in our KD tree is 4, since we have 4 features in the iris datasets. And then we run our model. For our KNN model, I'm using a K value of 5, meaning that I want to find the 5 nearest neighbors to each of my test data samples. I'll have more to say later about how to select the value of K when using the KNN algorithm. It's hard to tell if anything happened, but some amazing things just happened under the hood. Let's take a look at the output. It's a little difficult to interpret this output, but here's how to read it. This table contains 56 rows, which are the 56 samples in our test data subsets. The first column is the index number from the test data subsets that we extracted from the 150-element iris dataset. The second column shows the index numbers of the 5 nearest neighbors to each of the samples in the test data subsets. But the index number in the second column is not the same as the index number in the first column. The index numbers in the second column are from the 94-element training data subset that was mapped to the KD tree. So that 3 in the first column is the sample in the third row of the iris dataset, and that 3 in the second column is the sample in the third row in the training data subset. The third column shows the Euclidean distance between the test sample and its 5 nearest neighbors, sorted in order from closest to furthest. While this is certainly interesting, you may be wondering, how do we convert this output into classifications? This is where the post-processing comes in. The first post-processing step is to convert the list of nearest neighbors from a vector of vectors into a matrix. If you look in the REPL, you'll see what this code did. It converted the collection of nearest neighbors from a vector of vectors into a horizontal matrix, with each column showing the 5 nearest neighbors for each of the 56 test samples. Let's transpose this horizontal matrix into a vertical matrix so that it's easier to read. As you can see, all we did was convert that vector of vectors into a matrix that's easier to read. Now, we can use this matrix to find the class labels associated with each of these index numbers. So you can see what this post-processing step did. It converted the output and replaced the index numbers with the class labels. So the first row shows that all 5 of the nearest neighbors to that test sample have a class label of setosa. So that test sample is easy to classify as also being setosa. Now, let's take a look at row 53. That row shows 2 of the nearest neighbors have a class label of Virginica, and 3 of the nearest neighbors have a class label of Versicolor. In cases where the nearest neighbors have different class labels, the class with the most occurrences is declared the winner. So row 53 will be classified as Versicolor. But those classifications don't happen automatically. We need to write the code to do that. The countMap function comes from the stats-based package, and it counts the number of different elements in a collection. The argmax function comes from Julia Bayes, and in cases where there may be multiple maximums within a collection, it returns a maximal index. This is a little confusing, so let's take a look at a demonstration to see how it works. This is the row that we just looked at with the 2 nearest neighbors that are Virginica and 3 nearest neighbors that are Versicolor. The countMap function is like a histogram, but it creates a dictionary with a key-value pair showing the unique elements paired with their counts. And the argmax function just returns the index with the largest count, which in this case is Versicolor. So what's the difference between the argmax function and the maximum function? In this case, the maximum function returns the key value pair of Virginica and a count of 2. This is an example where there are multiple possible maximum values within a collection. Virginica is greater than Versicolor because it comes after it alphabetically. But that's not what we want. We want the key, or the index, that contains the maximum number that it's paired with. The argmax function can tell the difference, but the maximum function cannot. Now, let's check the accuracy of the predictions made by the KNN algorithm.
Wow!
So that's pretty amazing, right? We got an accuracy score of 96%, which is among the highest that we've seen so far in this tutorial series. Let's take a look at the misclassifications. As a reminder, the first column contains the predictions from the KNN model. The second column contains the actual label classes from the testing data subset. And the third column shows whether or not the predictions were correct. So our KNN model only misclassified 2 samples. Not too bad, right? Before we get carried away, let's run our model again using a different value for k. Go back up to row 156, or whichever row it is in your editor, and change that k from 5 to 11, and rerun your code until you recalculate the accuracy score. As you can see, the output shows 11 nearest neighbors as opposed to 5. As you might expect, there are now 11 columns showing the class labels of the nearest neighbors. You can skip the CountMap and ArcMax demos and go right to checking the accuracy of the prediction. It looks like our accuracy score took a big hit and dropped from 96% to 93%, so selecting more nearest neighbors didn't help. Let's take a look at the misclassifications. If you sort on column 3, you can see there were 4 misclassifications, which isn't terrible, but certainly not an improvement. So you can see that selecting the value for k is very important when using the KNN algorithm. Unfortunately, there's no established method for selecting the value of k. So here are some common sense tips when trying to decide the value of k. The value of k should not be too low or too high. In most cases, the value of k should be an odd number to avoid having tie votes. The value of k should be greater than the number of classes. Try different values of k to see how they impact the accuracy score. We didn't discuss this today, but feature scaling is very important when using KNN, since KNN is all about measuring distances. For the iris dataset, and for our example using random numbers, the units didn't matter that much, but you can imagine how important it will be to rescale your features if they have extremely different values. With that said, have fun using the NearestNeighbors.jl package. We started today's tutorial with a visual demonstration of how KNN and KD-tree work conceptually by plotting some data. After learning a little more about the details behind KNN and KD-tree, we used the iris dataset along with the NearestNeighbors.jl package to create a KD-tree to use with a KNN model in order to make classification predictions. Although our model generated some great results, it did require some pre-processing of data and some post-processing as well. We also learned that the KNN model is sensitive to the value selected for k, and there's no established science for how to select the optimal value. A couple of other notes about the KNN algorithm. It's non-probabilistic and it's very transparent, so it's easy to go through it to gain a better understanding of how it works. So there you have it, folks. Yet another exciting tool to add to your ever-expanding machine learning toolkit. When you get a chance, please remember to thank the developer and the contributors of the NearestNeighbors.jl package for sharing this tool with the rest of us by going to their GitHub page and leaving them a star. Well, that's all for today. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. If you like what I do, then please consider joining and becoming a channel member. New tutorials are posted on Sundays/Mondays. Thanks for watching, and I'll see you in the next video.